Hey everyone, how are you? In this video, we are going to solve the Leetcode problem of the day, and the problem is power of 2. It is a very easy problem to solve, and let us see how we can solve it. The given input in the problem is an integer n, and the range of this n is minus 2 is to power 31 to 2 is to power 31. The output we need to give is true or false. We need to return true if the given value n, which is the integer, the input integer, if the n is exact power of 2. For example, if the given value of n is 1, which is 2 is to power 0, or 16, which is 2 is to power 4, then we need to return true. Reason being, 1 is 2 is to power 0. That is, it is exact power of 2. 16 is 2 is to power 4. It is exact power of 2. When we say exact power, it means the power should be an integer. It should not be in decimal. But when we talk about 3, if the given value of n is equal to 3, we need to return false because we have 2 is to power 1 equal to 2, 2 is to power 2 equal to 4. 3 will come somewhere between 1 and 2, right? We have to take the power of 2 with somewhere between 1 and 2, and that will be equal to 3. So it will not be an exact power of 2. And that is why we return false. Now let us see the first way to solve the problem, and it is pure mathematics based. There is no extra thoughts here, it's pure mathematics, and there is a mathematical term which is exactly made for these kind of scenarios, which is called log. Basically, if you want to find the log of a number with the base, this will exactly be equal to the power. That is, if you take base to the power, whatever value of power here, that is base raised to the power, then this will be exactly equal to the number. This is what log is all about. When you take the log of a number for any base, it will give you a value power. And when you raise the base with this power, this will be equal to number. This can be applied here because base is 2 and power is something we need to find out, and the number is already given to us as an input. So we basically need to find out this particular value. We know the base, which is 2, we know the number. So if we try to find out log of n to the base 2, and if it is exactly an integer, then we can return true, else we can return false, right? Now let us see the scenario of how to solve this using maths, using log. Now if you talk about 1, 16 and 3, for 1 it is true, for 16 it is true, for 3 it is false. Now if you try to find out the log of 1 to the base 2, it will be equal to 0.0. Log of 16 to the base 2 will be 4. This will not be 16, this will be 4, 4.0. And log of 3 to the base 2, this will be somewhere between 1 and 2, and the value will be 1.58 something. But if I round it up in two decimal places, this will be 1.58. That is, 2 is to power 1.58 will be somewhere equal to 3. So this is the exact power, this is the exact power, so we return true and true. This is not an exact power, this is not an exact integer, so we return false. But programmatically, if you will notice, these all are decimals. So what we can do to find out are they exact integers or not, we can just take the ceiling value of this. That is what is the upper bound of this. Or even you can take the lower bound, that is the floor value. For 0, it will be 0. For 4, it will be 4, not 16, it will be 4. And for 1.58, it will be 2. What you will notice here is, the value is not changing when you are taking the ceiling value, right? It is 0 and 0, it is 4 and 4, but when it is not an exact power, the value has changed. It is 1.58 to 2. Or if you take the floor value, this will be 1. Still the value will change, right? So this is not an exact power of 2. Now let us see another method, which is called bit manipulation. In bit manipulation, we just need to understand about how bits work, how binary digit works for any number, especially for numbers which are exact power of 2. Basically, any number which are exactly the power of 2, that is, any number when represented as a power of 2 and that power is an exact integer, will have just one bit set, or will have just one bit as 1, all other bits will be 0. And that set bit is the most significant bit, or you can say it is the leftmost bit. Now let me show you some numbers which are power of 2, and let me show you how their bit representation or binary representation will look like. 1 is 2 is to power 0, 2 is 2 is to power 1, then 2 is to power 2, 2 is to power 3, 2 is to power 4, 2 is to power 5. All are exact power of 2s, and you will see that their binary representation looks something like 1, 1 0, 1 0 0, 1 0 0, 1 4 zeros, 1 5 zeros. So you will notice here that they just have one bit set, which is the most significant bit or the leftmost. Just one bit are set for each of these digits, right? All other bits are 0. Now let us see some numbers who are not exact power of 2s. These are the power of 2 numbers. These are some numbers which are not exact power of 2s. We have 3, we have 5, 6, 7, 9, 11. All these numbers are not exact power of 2s. Here you will notice that we have at least 2 bits set. For 3 it is 1 1, for 5 it is 1 0 1, for 6 it is 1 1 0, then we have 1 1 1, then we have 1 0 0 1, 1 0 1 1. So now once you know the pattern of the bit representations of numbers, especially for numbers which are power of 2 and numbers which are not power of 2. Now there is a mathematical fact here, and I will tell you what. If you reduce 1 from a number which is a power of 2, for example, let us talk about 16. 16 has a bit representation as 1, then 0 0 0 0. If you reduce 1 from this, it will be 15, the set bit will be unset and all the 0 bits or the unset bits will be 1 now. Basically, this is what the binary representation of 15 is. Now, if you take the bitwise AND of these numbers, it will be equal to 0. This will be 0, this will be 0, then this will be 0, 0 and 0, right? Because all the set bits are unset, all the unset bits are set. This happens when you take out 1 from any numbers which are power of 2. But this is not the same for numbers which are not power of 2. For example, if I talk about 5, to talk about 5, the binary representation is 1, 0, 1. If you take out 1, it is 4. In this case, you are not unsetting all the set bit, or you are not setting all the unset bit. 4 has the binary representation as 1, 0, 0, right? Now, if you take the bitwise AND, you will find that this is not equal to 0. 1 and 0 will be 0, 0, 0 will be 0, but 1 and 1 will be 1. So the bitwise AND is actually equal to 1, 0, 0, which is not equal to 0, right? This is the exact case for all the numbers which are not the power of 2. And the reason is they have at least 2 bits which are set. When you remove 1 from it, the first bit, the leftmost bit, which is the most significant bit, is never changed. 1 will always remain the 1. Because there are other bits which will get reduced because we are just changing 1 bit. Let's take another example. Let us talk about 11. In 11, we have 3 bits which are set, right? The first one, if you talk about 10, which is 1 less than 11, it is equal to 1, 0, 1, 0. Now you will notice that the leftmost bit is not changed. And that is why if there is a bit which is not changed, still if all other bits are 0, you will still not get the bitwise AND as 0. You will still have a chance to make it more than 0, right? So simply what we can do is we can say that whatever value of n is given, I just need to say n minus 1 and take the bitwise AND of these numbers. If it is equal to 0, then we need to return true. If it is more than 0, then we need to return false, right? Now, the question says that the input can be negative as well, because the range of n will be from minus 2 to the power 31 to 2 to the power 31. Basically, if you talk about negative numbers, for example, minus 2, there is no number in the world, if you say that 2 to the power that particular number will be equal to minus 2. So basically, negative numbers can be safely ignored. See, the thing is, if you are saying 2 to the power minus 1, this is exactly equal to 1 upon 2 to the power 1, which is 1 by 2. No power of 2 can make the number negative. So negative numbers can be safely ignored. Now let me show you the two methods to solve the particular problem. The first one is log. What we can do is, if the number is less than or equal to 0, we can directly return false. Else what I can say is n is equal to math.log2. That is, I want to find out the log of n to the base 2. Whatever is the value, I will assign it equal to n. And then we need to return n is equal to the ceiling value of n. For the numbers which are exact power of 2s, this will be equal. So it will return true, else it will return false. So we can solve it using this method. Also, we have this second way to solve the problem, the bit manipulation way, in which if n is more than 0, then we need to return not of n and n minus 1. Basically, we are taking the bitwise AND of n and n minus 1. This will be 0, then we need to return true, right? So I'm just taking the not of whatever I'm getting here. And if I'm not returning here, it means the number is negative. In that case, return false, right? So I think that's it for this video, guys. These are the two best methods to solve the problem. We can solve the problem using recursion, binary search, using loops. But the question says that try to solve the problem without any loops or recursion, right? So we have tried to solve it completely using maths, and this problem is all about mathematics. So that's it for this video, guys. I will see you guys in the next video. If you like this video, if this video helps you in any way, then make sure that you hit that like button. And if you have not subscribed yet, then make sure that you subscribe to the channel as well. And I will see you guys in the next video. I want to see you guys in the next video. Thank you for watching this one.